Hi, this talk is about static analysis of memory using separation logic and using abstract relations as procedure summaries. This is joint work with Hugo Illous, Xavier Rival, and myself, Mathieu Lemaire. Many static analyses are state analyses. They compute an abstract state, which represents the set of reachable states of the program, and they can verify state properties, like, can this program perform a null pointer dereference? Or, does this program preserve structural invariance of data structures? Like, is this a linked list? Is this a red-black tree? Another kind of static analysis are transformation analyses. They compute abstract transformations, which are relations between the program input and the program output. They can answer to questions like, does this program modify the linked list received as an argument, or is it read-only? Is this sorting algorithm in place, or does it deallocate the list and create a new one? In this work, we will work on transformation analysis, and more particularly, we will see how abstract transformations can be used as procedure summaries, and we will do that in the context of shape analysis of memory using separation logic. Let us see how this works using an example that will be used throughout this talk. The append function inputs two lists, L0 and L1, and it modifies the last cell of L0 so that it points to L1. The double append function takes three lists, key0, key1, and key2. First, it appends key1 to key0, and then it appends key2 to the list formed by key0 followed by key1. Let's say we want to perform a state analysis on this running example, starting from the initial state H0. When we want to analyze the call to append, one way to do this is to propagate the state inside the body of append. Here we have a lot of operations to do in append because there is a while loop. Then we can return. If we want to analyze the second call to append, we have to do all this work all over again. On the plus side, this is very precise. On the negative side, the analysis of append is repeated for each calling context, and this can be very expensive. Also, this cannot handle recursive procedures. Now suppose that we have an abstract transformation describing what append does. This abstract transformation is a relation between the input state and the output state of append. Now, by applying this abstract transformation to the state which is before the call to append, we can get the state which is after the call to append. And we can do this several times without having to reanalyze the body of append. Thus, applying an abstract transformation can considerably speed up a state analysis. Now we will do things differently. We still have T, which is the abstract transformation describing what append does. And we still have H0, which is the initial state for double append. Now ID of H0 is a transformation that does nothing to states described by H0. If we compose T two times with this ID of H0, we get a relation between the input state of double append and the output state of double append. Thus we obtained a summary for double append. Let's now focus on a specific state abstraction, which is a shape abstraction based on separation logic. What this formula describes is three linked lists. Key2 points to any linked list. Key1 points to a linked list, which is non-empty because this is the last cell. Key0 is also non-empty, and this is its last cell. Now we perform a state analysis by inlining again and propagate the state inside append. And after, this is what you obtain. The last cell of the first linked list points to key1. Propagate the states for the second call to append. After this, we have modified the last cell of the key1 linked list to point to key2. We will reuse an abstract transformation published in an earlier paper, which describes how to compute an abstract transformation for a given initial state. What this abstract transformation describes is two linked lists. The second linked list can be any linked list and is not modified by the function. The first linked list must be non-empty, and its last element contains initially 0 and is now modified to point to the second linked list. the rest of the linked list is not modified. Using this abstract transformation, we could use it to speed up the analysis of the double append function. But instead, we will compose abstract transformation to get an abstract transformation describing what double append does. So what this computed abstract transformation describes is that double append works on 3 linked lists. The key 2 linked list, it can be any linked list and it's not modified. Key 1 is a non-empty linked list and is modified so that its last element now points to key 2. And key 0 was a non-empty linked list and is now modified so that its last element points to key 1. So this is also an accurate description of what double append does. Our contribution describes an interprocedural transformation analysis based on separation logic. So we will first describe how we can compose our shape abstract transformations. And then we describe how we can build our interprocedural analysis on top of it. Then we'll show our evaluation on parts of Emacs code. So we begin by describing the composition of shape abstract transformations. Our abstract transformation is based on separation logic. Separation logic describes properties on memory states by combining descriptions of single memory cells and of complex data structures. Our relational separation logic extends the separation logic and describes the properties of pairs of states, of an input and output states. There are 3 kinds of relational separation logic connectives. The first is ID, absence of modification. It takes an input state represented by H and in which the output state is the same. The second is memory transformation. It takes an input state represented by HI and the output state has been replaced by a state represented by HO. The last connective is independent transformation, where we combine 2 transformations, T0 and T1. We do that by merging the input states of T0 and T1, merging also the output states, in a way that everything coming from T0 is separated from everything coming from T1. So the composition of abstract transformations consists in executing both transformations in sequence. So for instance, if we have a transformation that goes from H1 to H2 and another which goes from H2 to H3, the result of the composition is a transformation which goes from H1 to H3. Sometimes for reliability, we use the reverse composition operator, which swaps the order of the arguments. Abstract composition is sound if it over-approximates composition, meaning that if there exists a common sigma 2 allowing to go from sigma 1 from sigma 2, 3, then the pair sigma 1, sigma 3 must belong to the composition. Let's see how the composition of abstract transformations works on an example. This is the relation that we have before the first call to append, and this is the summary for append. And we want to compose them. The first thing that we do is that we split the shape separation and we transform this into a relational separation. Both forms are equivalent. This allows to split the composition into 3 separate compositions. In the first case, we do no transformation on the linked list twice, so the result is just a linked list which is not transformed. Here is more interesting. We have a linked list which is non-empty, which is not modified, and the second transformation is any linked list which is also not modified. The composition uses the intersection operator of abstract state, so the result is a linked list which must be also non-empty. For the first linked list, we also do split the shape and introduce a relational separation. Here, the composition is also simple, and here we compose a a single memory cell which is not modified with a memory cell which is changed from 0 to points to the second linked list. Well, the result of the composition is also a transformation which modifies the cell from 0 to point to the second linked list. And we get the final result. Let's now see how we can use composition to build an interprocedural relational analysis. Our interprocedural analysis does not compute a summary that will be valid for any context. Instead, it computes a context transformation summary, which is a pair, HT, where H is the context in which the summary may apply, and T is the abstract transformation describing what the function does. So HT is a sound context transformation summary for procedure C if, when we represent the semantic of the procedure by a set of pairs, input, output, then if the input is belongs to the context, then the pair belongs to the transformation. For instance, this is a sound context transformation summary for append, but it only applies to lists that have only one element. The legitimate question is, why do we need both a context and a transformation? It could well be that we could extract the input state from the transformation. And indeed, in the case of the summary of append, which works only for a linked list of a single element, we can extract from this transformation this input state. In general, this does not work. Indeed, the abstract transformation needs only to include the input state for which the procedure returns, and not the other input states. For instance, if we analyze append for this initial context, where L1 and L0 can be any linked list, then the analysis returns this abstract transformation, where L1 can be any linked list, but L0 must be a non-empty linked list. So the analysis has correctly inferred that the function does not work if L0 is empty. Thus, we need both the context and transformation if we want to use a summary in all the contexts where it can be used. Otherwise, sometimes we could miss some cases where we could use the context, and it can even lead to non-termination. So let's now see how the interprocedural analysis works in the case where summary is available. So here we have a summary for the append function with the same abstract transformation as before, and a context which is any pair of linked lists. We reuse the same input relation for the call to the first append function. So the first thing that we do is that we copy the parameters. So key0 will be copied to L0, and key1 will be copied to L1, which are the arguments of the append function. Then we extract the output state. In this case, it is rather easy. We just have to remove the ID connective. Then we take the reachable part, the part of the memory which is reachable by append. So append can reach everything which can be linked from L0 and L1. But the third linked list is not passed as an argument to append, so it's not reachable by append. Now we check if the reachable part is included in the abstract context for the summary of append. In this case, this is the case. Then we can apply the summary. The first thing that we do is that the non-reachable part will not be modified, so we put an ID around it. Then we put the transformation part of the procedure summary of append. And we use the composition algorithm that we showed earlier. This is the result of the composition. Now we can remove the parameters L0 and L1, and we obtain the relation between this program point and this program point. So now what happens when the context for which we have the summary is not general enough? Here we have a summary for append, but it only works for the case where the second linked list has only one element. The first steps are exactly the same. Now, this context does not cover the reachable part of the input, because here it can be any linked list, any non-empty linked list, and here it must have only one element. So what do we do in this case is that we just compute a new input context by joining and widening the already existing context with the new one. From this we can compute a new abstract transformation, and now we know that this abstract transformation works in the context of the call, so we can just apply it and perform the composition like we did before. Let's now see how our interprocedural analysis works in practice. So we implemented our analysis as a plugin for the Flamacid platform. We implemented three different modes. The first is state analysis, where we fully inline the function calls. The second is a relational analysis, but we also inline the function calls. And the last one is a relational analysis, but where we use and compute procedure summaries. We experimented mostly on the parts of the Emacs code. It's a part of the code which is everything below the fx show type function. And in total it is 2000 lines of C code. And so Emacs is mostly a Lisp interpreter, and this code is does heavy manipulation of pairs used as untyped linked lists. Here are the results of the experimental evaluation. While the relational analysis takes more time than the state analysis, it allows summaries, and the summary-based analysis is much faster than inlining analysis. 60 times faster than the state analysis, and around 300 times faster compared to the relational analysis with inlining. And this happens for each function. On this graph, each dot represents the analysis time in the summary-based analysis and in the state analysis with inlining. And we can see that except for the very small functions, all functions benefit from using a summary. Also, most functions were analyzed only one time. The only one which was analyzed 3 times was the cons function, but it is used 47 times, so the summary still wins. We did not observe any loss of precision in the summary-based analysis compared to the state and relational analysis. While this is theoretically possible, it did not happen in our example. And the relational analysis allows to infer properties that are stronger than state properties, for instance, to show that some parts of the memory is not modified. Finally, the method also computes abstract transformations for recursive functions, and we describe in the paper how we can modify the algorithm to do that. Let's now conclude. Thus we show that contextual procedure summaries can be represented as an abstract transformation in a specific context. That we can perform summary-based transformation analysis by composing abstract transformations, and that this works well in the context of memory analysis using separation logic. To conclude, transformations are harder to abstract than states, but they are very useful, and using them can be very rewarding. They can be used for compact and precise function summaries. They capture a natural abstraction for programmers, and they can verify useful functional properties, like is this function read-only, or is this sorting algorithm in place. Thank you.